The chain rule is used to find the derivatives of composite functions. Given two functions, g and f. F composed with g, at x is defined by f of g of x. The derivative of f of g of x, of course, depends on the derivatives of both g and f. In fact, it is the product of their derivatives, evaluated at the corresponding inputs. The derivative of g at x is g' of x. And the derivative of f at g of x is f' of g of x. So, the derivative of f of g of x is equal to g' of x times f' of g of x, which can also be written as f' of g of x times g' of x. This is the chain rule for the composition of two functions. This rule can be generalized to the composition of any number of functions. Let's consider the composition of three functions, f, g, and h. First, we take the derivative of the outermost function f, keeping the same input g of h of x. This is the first factor in the chain rule formula. We are done with the derivative of f. Now, we focus on g. We take the derivative of g, keeping the same input h of x. This derivative becomes the second factor in the chain rule formula. We are now done with the derivative of g as well. Finally, we differentiate h of x to get the last factor in the chain rule formula. This completes the chain rule formula for the composition of three functions. In the chain rule, each function in the composition acts like a link in a chain. To find the overall derivative, we take the derivative of each link and multiply them together. Now, we will apply the chain rule to find the derivatives of some composite functions. Let's use some known derivatives. We compose the fifth power function, the square root function, and the reciprocal function each with the linear function 2x minus 7. And find the derivatives of resulting composite functions. To find the derivative of 2x minus 7 to the fifth power, we need to apply the chain rule. First, take the derivative of the outer function, the fifth power, and evaluate it at 2x minus 7, the inner function. This becomes the first part of the derivative of the composite function. We have completed the derivative of the outer function. Next, differentiate the inner function 2x minus 7. Its derivative is 2, which becomes the second and final factor in the derivative of 2x minus 7 to the fifth power. Now, we find the derivative of the second composite function, square root of 2x minus 7. First, take the derivative of the square root function and evaluate it at the given input 2x minus 7 to get the first factor in the derivative. This completes the derivative of the outer function. The derivative of the inner function 2x minus 7 is 2, which is the second and final factor of the derivative. Now, we find the derivative of the last composite function, 1 over 2x minus 7. First, take the derivative of the outer reciprocal function, keeping the same input 2x minus 7. This becomes the first part of the derivative of the composite function. We have completed the derivative of the outer function. The derivative of the inner function 2x minus 7 is 2, which is the last part of the derivative of 1 over 2x minus 7. Finally, we simplify each of these derivatives. Now, we will see how the order of composition affects the application of the chain rule. Let's consider the compositions of sine of x and x squared in different orders. Note that the square of sine of x is written as sine squared x. Now we find the derivatives of these composite functions, using the chain rule, and the derivatives of sine of x and x squared. First, we find the derivative of sine of x squared. This composite function has sine as the outer function, which is differentiated first. The derivative of sine is cosine, which we evaluate at the given input x squared. This is the first factor in the derivative of sine of x squared. We have computed the derivative of the outer function. The derivative of x squared gives the remaining factor in the derivative of the composite function. Now, we find the derivative of sine squared of x. Again, sine squared x is same as the square of sine x. So the outer function in this composition is the square function, which we differentiate first, and evaluate at the given input sine x. This is the first factor in the derivative of sine squared x. We have computed the derivative of the outer function. The derivative of sine x gives the remaining factor in the derivative of the composite function. This example illustrates that the derivatives of composite functions can vary significantly, depending on the order in which the functions are composed. Now, let's discuss the derivative of a more complex function created by composing several simpler functions. It is the composition of polynomial, logarithmic, square root, tangent, and exponential functions. We apply the chain rule to differentiate this composite function, starting with the outermost function and proceeding inward. Note that at each step, the derivative of a function is evaluated at its corresponding input. The outermost function in this composition is the exponential function, which is differentiated first. The derivative of e to the x is e to the x. However, we need to evaluate it at the corresponding input. This becomes the first factor in the derivative of the composite function. We are done with the derivative of the exponential function. Now, we differentiate the tangent function. The derivative of tangent of x is secant squared x, which we evaluate at the corresponding input. This becomes the second factor in the derivative of the composite function. We are done with the derivative of the tangent function. Now, we need to differentiate the square root function. The derivative of the square root of x is 1 over 2 times the square root of x, which we evaluate at the input of the square root function. This becomes the third factor in the derivative of the composite function. We have completed the differentiation of the square root function. Now, we differentiate the logarithmic function. The derivative of the natural logarithm of x is 1 over x, which we evaluate at the given input of the natural logarithm. This becomes the fourth factor in the derivative of the composite function. We have completed the differentiation of the logarithmic function. Finally, we find the derivative of x to the 4 plus 7, which is 4 times x cubed. This is the last factor in the derivative of the composite function. Thus we have completed the differentiation of all the functions involved in the composition. Finally, we simplify the derivative.